Welcome everyone to the ICANX Talks. My name is Sang-tae Kim from Hanyang University in Korea. It's my honor to be the moderator of today's ICANX Talk sessions. I myself am a recipient of the ICANX Young Scientist Award in 2020, and it was a great honor. It's also a great honor to serve now as the moderator. So let me briefly introduce this week's or April's iConnect sessions. Today we have Professor Rusen Yang from Xidian University. And unfortunately, Professor Shastri from Queen's University could not join today. So we will only have one talk from Professor Rusen Yang. But I'm sure he will give a wonderful talk. So today's session will be great. So please look forward to it. And next week, we have Professor Xue Feng from Tsinghua University, followed by Professor Sarah Bales and Professor Bumjun Kim in April. So that's going to be, and also today we will have Professor Haisha Ellis Zhang as a panelist alongside me, who serves as the moderator. And we apologize, we couldn't really change the picture for today's advertisement. So let me introduce today's speaker, Professor Rusen Yang. Professor Rusen Yang is a Hua Shan professor and vice dean at Xidian University in China. He received his PhD in material science and engineering from Georgia Tech. And from 2010 to 2018, he worked as an assistant professor in the Department of Mechanical Engineering at the University of Minnesota. He has focused his research on synthesizing new nanomaterials and exploring their applications for energy harvesting and sensing applications. He has a wonderful track record with publications of over 150 papers in peer-reviewed journals, and he has been cited for over 12,000 times. I'm very envious of that number. And his transformative work has won him NSF Career Award, 3M NTFA Award, and Nano Energy Award. So let's please welcome Professor Rusen Yang with wonderful big hands. Professor Yang, the stage is now yours.
Thank you. So I will share my screen right now. Okay, give me 1 second. Professor Kim, can you see my screen?
Yes, I can see your screen fine, and it's coming up on the official website right now, I think.
Okay, great. And first, I would like to thank Professor Alex Zhang for her invitation and to give a talk at this wonderful, ICANX talk platform. And I also want to thank Professor Kim for his, very nice introduction. I will spend the next 1 hour or so to share my work I have been doing in the past few years. So today my talk will mainly based on the biomolecular-based piezoelectric nanomaterials and their energy harvesting applications. Okay. So before we talk about I would like to introduce you to my university, the Xidian University. And this university is located in Xi'an. Xi'an is one of the oldest cities in China. It is also the starting point of the Silk Road and an ancient cultural city with numerous historical sites. And for example, this is a world-renowned terracotta warrior. I know many friends like to visit Xi'an and like to visit terracotta warrior. In addition to that, we also have the Science History Museum, and also the White Goose Pagoda, and also the city wall. The city wall is also very interesting site. Unfortunately, I have not visited myself yet. So I would like to invite everybody from the world visit Xi'an and maybe visit my group so that I can go with you to walking on the city wall, and so that we can enjoy, inspiring discussion and also the beautiful view of the Xi'an as well as Xidian University. And here is the outline of my today's talk. First, I would like to talk about what we are working on and why, so that will be our motivation. Next, we will talk about the fabrication and characterization of biomaterials, the biomimetic materials from self-assembly of those different amino acid and peptide, etc. Next, we will talk about the peptide-based nanogenerators, followed with the summary. So let's talk about what we are working on and why. My group is mainly work on the nanomaterials. As a matter of fact, I have been working on the nanomaterials over 20 years, many years. I like nanomaterials. And in addition to synthesize the new materials, I'm also interested in studying their properties and fabricated devices. They are all kind of interesting properties can be discovered from the nanomaterials. For example, so what I'm interested in, including the mechanical property, electrical property, piezoelectric property, etc. And for the device point of view, my group is mainly focused on the energy harvesting, energy storage, sensor, etc. Definitely, there are many more interesting properties can be found from those materials and more devices, such as optical property, magnetic property, etc. And accordingly, there are many more devices can be fabricated from these devices. So I'm kind of open-minded and also would like to collaborate anybody who interested in this area, and so that we can work together. Here is some materials I have been working on, and here is mainly the inorganic materials such as zinc oxide, tin oxide, zinc phosphide, aluminum nitride, and many years ago I also worked on the back in the 1998 work on the single wall carbon nanotubes, and nowadays I also work on some 2D materials like molybdenum, the sapphire, etc. But at early time, zinc oxide has been my favorite material, and now it still is one of my most favorite materials as well. And I have, fabricated different nanostructures from the zinc oxide materials, such as nanowires, nanorings, nanospring, etc. So I really like the picture of the ring. It's kind of a lot of the ring in the nano world, right? And but in the past few years, I also found another interesting material. So that would be biomaterials. And so because in the past I mainly focused on the piezoelectric property, and that's why I mainly work on the piezoelectric ceramics. But later I find out, biomaterial is also very interesting. Why? Because they are bio, they are smart and green. And because they are, bio nature, they have some biofunctional growth like amino acid, etc. It can be used for some biosynthesis. Many biomaterial crystals have the porous crystal structure, so they have also been shown to use for the electrochemical, drug delivery, optical, etc. Most importantly, as I earlier said, I like piezoelectric material, and the reason I'm interested in the biomaterial is some biomaterials have also strong piezoelectric property. And for example, our bone, like our cheese, the bone is also piezoelectric material. Many materials are piezoelectric material, can be found in our body. So since they have a strong piezoelectric property, they can also be used to fabricate piezoelectric devices. So, got my interest. I'm trying to work on the new area and fabricate some new material, new structure from the biomaterial. Hopefully, we can find some interesting applications as well. And here is kind of a summary. And for the summary from the synthesis, property, morphology, and application. And we start from some biomolecules, for example, the amino acid and peptide, etc. And amino acid, we need the amino acid, every day. It constructs the peptide and eventually form the protein and form the tissue, form the organ, and eventually form our human body. So amino acid, they are biomolecules, and when we digest many the nutrients eventually will metabolize form the amino acid eventually. So amino acids, they are biomolecules, and I'm not using this material just for their biosense. So I'm trying to use them to form some functional material. And how to fabricate? There are all kind of different methods. On the top right, I noted point out we have vapor based method. We can also have the solution based method, and eventually in those through those methods, you can got through the so-called self-assembly process to form the material. What kind of material can form? On the top left, we can notice that you can have the nanospheres and quantum dots and fibers, nanotubes, microtubes, and nanoplates, etc. And many interesting properties has also been discovered in the biomaterials, like earlier I said, the piezoelectric property. In addition to that, clearly people interested in their biocompatibility, optical property, etc. And using their different properties, people explore the different applications, such as anti-harvesting and biosensing, and also some tumor diagnostics, etc. Next, we will talk about the fabrication and the characterization of the material. Without the material, we cannot do anything. So first, we need to fabricate the material. How can we get those interesting nanostructures or macrostructures? And first, when I start in this area, start working on this, new material, I also be think about what are current challenges, right? And people already know the piezoelectric property. Why there are not many piezoelectric applications using these biomaterials? First is due to the lack of the scalable alignment method. And even you manage to align them and still lack the control of polarization. So what's that mean? So because of piezoelectric properties, they are not, kind of anisotropic, right? Just like batteries, you have the positive side and negative side. So they have the direction. So when you put the different nanomaterials or macromaterial together, they may point into different directions, like in the bottom picture. You have a different nanowires or nanofibers, and they look like they all fibers, but they have the different color. What's that mean? That means they have a different direction, like here. So right, so just like a battery, the battery pointing in this direction, and this battery pointing in this direction. If you put them together, they just cancel each other. So this is so-called polarization. They have the different polarization, so that when you put them together at the microscopic level, the piezoelectric effect will be much smaller. Ideally, people should have the aligned structure with the aligned polarity. The polarity is more important than the physical alignment. So this is the tricky part. And people, some people may work on the piezoelectric ceramics, and maybe some people know the piezoelectric ceramics. They also polar, crystal. What does that mean? That means the piezoelectric crystal, piezoelectric ceramics, the polarization, they're totally random. But why people can still use the piezoelectric ceramics for different applications? The reason is even though the piezoelectric ceramic, all those the particles inside, they have random polarization. People have the so-called polling process, and what that means, they just apply very strong electric field. And so at the high strong electric field, all the polarization will be switched and aligned in the direction of the electric field, so that after the polling process, all the polarization will be aligned in one direction. So that's why people can use the piezoelectric ceramics, although they are polycrystal. They start with random polarization. Will this polling process work for biomaterials? And we put it into test. First, we fabricate the material. It's quite simple. So we just have some FF solution, diphenylalanine solution put on substrate. They form amorphous film. We put this amorphous film in a moisture environment. It will be crystallized. We use this crystallized film as a seed layer, then put it in a solution to start the epitaxial growth. And then we form the macro rod arrays. The XRD X-ray diffraction measurement confirms that they are crystal material. They have the hexagonal structure. That is what we want. They should have the piezoelectric property. That's good. So far, so good. So how about the polarization? We did the measurement with PFM, the so-called piezo response for the microscopy. And this is the fourth phase scan. Here you can see we have the mainly two phases. One is around 0, the other is 180. What does that mean? That means, about half of the macro rod have the polarization upwards, the other half is downwards. It's even, more clear on the right. We have the yellow region and we have the violet region. That means, one is pointing downward, the other half is pointing downward. Basically, if you use this as a piezoelectric material to fabricate devices, just like a battery, half of is pointing upward, the other half pointing downwards, and they will cancel each other. So that is not good. And could we apply strong electric field so that to switch all those polarizations so that they align in one direction? We did some tests. And as shown here, we have two materials. One is for the blue, the other is red. The blue is PPLN, that is periodically polarized lithium niobate. So that is very traditional, conventional piezoelectric ceramic. It's widely used for nonlinear optics. And for the PPLN, we can clearly see we can switch the polarization from one direction to the other, very relatively easy, right? But however, when we apply the electric field on the F5 self-assembled macro rod, it stays in one direction. The highest electric field is around 4 millivolt per meter. That's a very strong electric field. But the polarization is still reluctant to switch. Basically, the polarization cannot be switched as in the piezoelectric ceramics. If you apply any higher, you can imagine the electric field is already very high, and it will be damaged. So now look like, although the FF micros are piezoelectric materials, we cannot use them because the polarization, they are random. Okay, what can we do? And we think about after we fabricated the material, we cannot got unified uniform polarization. How about what happens if we apply electric field during the self-assembly process? Okay, just like here, we know the FF molecule, they are dipoles, right? They are polar molecules. They have the dipoles. If we apply electric field during the growth, okay, during the growth, could all those molecules will be aligned in one direction under the influence of the electric field, and so all those aligned molecule will start a self-assembly and form a macro rod or whatever structure and with uniform polarization. So that is our hypothesis. We put it into test and grew the FF macro rod with the electric field applied during the process. And we still got the macro rod. There are no difference. How about the polarization? Now, when we use a PFM to scan the surface, we got only one color. That's good. So that means we have a uniform polarization. All the polarization in one direction just, agree with the electric field. How about we switch the electric field in the other direction during the growth? What will be the macro rod? And look like the macro rod still, physically there's no difference, but the polarization switch. Look like although we cannot switch the polarization after the growth, we can control the polarization by applying electric field during the growth. So we found a way to get piezoelectric biomaterials with uniform polarization. Then we can start to investigate the piezoelectric effect in the biomaterial and eventually to fabricate some devices. What is the piezoelectric property of those FF macro rods? And we measured their piezoelectric constant. And the D33 value tell us for the earlier material that is around between 10 picometer per volt to 18 picometer per volt. And put this one into aspect how this property compared with other materials. And we know for some in piezoelectric ceramic like PZT, they can have 100 of picometer per volt, but that is different. How about my earlier favorite material, zinc oxide? Zinc oxide have a piezoelectric constant around 12 picometer per volt. That will be this value. Look like the FF macro rods have a comparable piezoelectric property as the zinc oxide. So that's pretty good. That's really encouraging. And some material even higher, reach 18 picometer per volt. So that is even better. We really like it. And then from that time, this is earlier paper published in the 2016. And after that, I spent most of the time working on the self-assembly of biomolecules to find some new materials, measure their properties, and try to fabricate the devices. The purpose is got the material with better property and fabricate a better device. Before, we did two things. One is do the synthesis. At the same time, we also did some computation. Peptide is one thing, but we know the peptide is formed from the amino acids. So we also did some computation of amino acid. Could amino acid also self-assembly into some crystal structures, and does those structures have some interesting properties? And we did some computation of amino acid crystal. Here are some examples. For our body, we normally have 20 natural amino acids. Okay, so here is 3. It will be valine, methionine, and leucine. Okay, and we did definitely we did computation of much more, many more different material. Here are just three examples. And for the vanillin, methionine, and the leucine, they have a kind of a different chemical structure, but they are quite similar. They all belong to one type of the amino acid. We know for the amino acid we have the different types like the polar, non-polar, acid, basic, aliphatic, etc. So this is the one type. And from the calculation, they have this type of crystal structure. We also calculated their band structure, and we also calculated the Young's modulus, etc. And it look like it is not surprising. Most of the biomaterial have a very wide band gap, like over 6 electron volt. They are dielectric material. They are not conductive. However, there could be some good, interesting optical material. So that is a different story. We will not cover that one. And very interestingly, during the calculation, we noticed that some of the amino acid can form some crystal structures with pretty narrow band gap, like for the methionine. So the band gap only 2.88 electron volts. That's within the wide band gap semiconductor regime. So maybe this material can also be used as semiconductors. My group is still working on that. And another property we calculate is Young's modulus. Okay? We also calculate some, the Young's modulus to see what is the mechanical property, right? We want this material robust. We do not want this material too fragile. And it look like the self-assembly of the amino acids also got a pretty good Young's modulus. And from this one, we continue to calculate the piezoelectric property. We're pretty happy with the result. Look like some of the material got a very high piezoelectric constant. For example, earlier, probably you still remember the highest piezoelectric constant is only 18 picometer per volt. But from this amino acid, the highest one is over 50, right? It's already over 50 picometer per volt. So it got a very good potential to work as piezoelectric materials. This calculation give us some confidence. We continue to work on this material, try to get better and material and device. So that is just the computation. How about the real world? We also started to do the synthesis of those materials. Just for those three, the same amino acid, the valine, methionine, and the leucine. And we still use a solution-based method because this is quite simple, right? So our body, doing all those synthesis under the 38 degrees Celsius, right? Very low temperature, very environment friendly process, right? So in the solution. So we just simulate the body. We use a solution-based process to synthesize those different material. Quite simple. We just put all those raw material in water to form the solution, and we put some other, solvent in the solution so that the material, the different material will start to self-assembly, precipitate, and form the crystals. And the temperature is around, also very low temperature. From those valine, methionine, and leucine, what we got is some crystals. So this is a plate, not like the FF. Early FF we got a macro rod, but for this material we got a lot of plate, a micro plate, and sometimes it's also the nano plate. Some the thickness, some is thick, some is thin. It really depends. But we also, use XRD to study the crystal structure, and we also study their thermal stability because we're worrying about this organic material maybe not that stable under the different, under the heat. Look like they are quite stable. We did the measurement. It clearly stable around 200 degrees Celsius. It can even survive a even higher temperature. That's really good. And we also did a further study. Because for the self-assembly, the non-covalent bonding is really important, like hydrogen bond, van der Waals bond, van der Waals interaction, and the pi-pi interaction, etc. So the non-covalent interaction is really important. So what is who play important role in the self-assembly process, and how about those interaction related to their physical property, right? So we don't know. We did some computation and also the measurement. For the computation, there are the so-called Hertzfeld surface. This analysis is an efficient tool to analyze interactions between atoms in crystal structures by partitioning the crystal space occupied the molecule into the non-overlapping and interlocking molecular volume based on their crystal electron density. As shown here, we have some red spots. We also have some blue areas. The red spot on the surface near the oxygen atom represents the strong interaction between the oxygen and the hydrogen atom. And the blue area indicates some the weak interaction contributed by interatomic contact with the distance beyond the van der Waals distance. Okay, so this Hertzfeld surface can tell us the atom-atom interaction. And this column gives us the 2D, two-dimensional, the fingerprint plot, so that people can clearly see all those interaction. And this is maybe abstract, and we did some statistics. So we have this the so-called the pie chart, right? The pie chart you show us the molecular interaction of the amino acid. Okay, and from this one. And from this pi interaction, we can clearly see, the red and the yellow area, and corresponding to OH and HO, the interaction look like the who has the highest one. Clearly, the valine has the highest the value around 39.9%. And it's then followed by methionine, that is around 37.2, and the lowest one will be the leucine crystal, so that is around 30.8%. So basically, the non-covalent interaction is strongest for the valine, followed by methionine, and then leucine. And here in this case, it's mainly contributed by the hydrogen bonding, right? Maybe put it simple, the hydrogen bonding is strongest in the valine, followed by the methionine and the leucine. So they have the different hydrogen bonding. And how about the hydrogen bonding related to the mechanical property? We can clearly see the Young's modulus also follow the same trend, right? The highest hydrogen bonding, the higher Young's modulus, that is around 10 gigapascal, and the methionine, that is around 3, and the leucine has the weakest hydrogen bonding, that is 2.6. And from this study, we believe the hydrogen bonding is related to its property, like its mechanical property. How about other property? And we also did did some measurement of their piezoelectric property, etc. Okay. In addition to the Bhavin, Masani, and Rusen, we also synthesize some other amino acid. Early we have the phenylalanine and the dopa and tyrosine. Okay, so they are also important amino acid. The reason we started this one is early you can see in order to do the self-assembly we need put this material in water to form a solution. However, the tyrosine have a very low solubility, so that is almost 2 order of magnitude smaller than some other amino acids. So it's really kind of insoluble in water. However, when you put some amyloid inhibition agent in the solution, that will increase the tyrosine's solubility. Okay, and eventually we can fabricate some fibers from the L-tyrosine. Okay, and so that after you got the material, then you can start to study their properties. And here is the mechanical property from these 3 material. We can do some comparison. If you still remember, like for the other 3, the Young's molecules is only around 10 gigapascal. How about this one? The phenylalanine is still around 13.6, and dopa is 56. And earlier we said that tyrosine, this material is really reluctant to solve in water, but after you put some agent, we can manage to make it more soluble and eventually to got some material. Its Young's modulus is significantly higher, and this is over 100. 157 gigapascal. We put it in the perspective. Here is some common materials and they are Young's modulus, and we have actin and collagen. If you like some seafood, probably actin, and if you like care about your skin, we have the collagen, because people believe collagen is better for your skin, all right, make it smooth, etc. Right, and we have the amyloid, the silk, the bone, the glass, and the steel, right? So they have the different Young's modulus from very soft one to very stiff one, right? And here is the Young's modulus of phenylalanine, dopa, and tyrosine. We can clearly see, the tyrosine got a very stiff, right? The Young's modulus is extremely high, right? Well, extremely high. It's really surprising because this is a biomaterial. How this biomaterial can have such high, the Young's modulus, right? And so we still continue to study the mechanism because some of the material, so very surprising property, and we try to study the mechanism. And earlier we did the self-assembly with only one component, like FF diphenylalanine, or maybe only one type of the amino acid. What happened if we put different material in the solution? Could you get the co-assembly? All right, co-assembly. I think probably it's possible because in our body the amino acid, it never exists, just by itself. They always connect together to form a different peptide, right? They have a different series, okay? And in this study, we have the FF, FW. W is tryptophan, right? Another different amino acid. And we have the cyclo, FW and FMOC, FF, etc. And we can put them together in the solution, try to get a co-assembly. If we put only FF in the solution, we can also get the different fibers, right? We studied their, the influence of the temperature, etc. Okay, and we started to mix FW with FF to see what happened, and it look like the area coverage they are changed, right? When we only have an FF, the area coverage is this much, less than 80%, around maybe 70, right, 75. When we put in FW inside the solution, the coverage are higher. That means the yield got higher. Okay, and then start getting less. Okay, we get less and less structure. Okay, look like they are relevant. And we started their crystal structure with XRD. Okay, and when we zoom in, we find out their parameter, crystal parameter also changed, right? And because FW, F and W, they are not totally the same. Okay. We did the chemical analysis with the time of flight secondary ion mass spectroscopy, and to study their use mass spectroscopy. We've studied their chemical analysis. Okay, look like from the bottom we can clearly detect the signal FF. No wonder. At the same time, we also find the FW. Use mass spectroscopy, we did identify different material. And we also did the image. Optical image look like this one. And if we only select the FF channel, we have this picture. FW channel, we have this one. When we overlap, it look like they have a pretty good overlap. Right? This start confirm we can have the FW and FF co-assembled fibers. Okay? And we studied the optical property and as well as piezoelectric property. And from this study, we can see we got the highest piezoelectric constant around with 20% FW. This study tell us a strategy to increase the property of the self-assembled non-structure from the biomolecule using the so-called co-assembly process. If you have one type of material, you got some interesting property. When you mix them together, maybe you got some better one. Earlier, we mainly focused on solution-based process, and here I would like to briefly talk about the vapor-based process. Right, the solution is simple. But when I work on the zinc oxide, I'm mainly using the vapor deposition process, physical vapor deposition, chemical vapor deposition, etc., and have the biomaterial. The biomaterial is a little bit tricky, okay? Because this material cannot survive, extremely high temperatures because they're bio. Eventually, you will just burn them, right? And they have a strict control of the growth parameter, but it's still doable. Okay, and in this case, we tried valine, leucine, isoleucine. Okay, and then we got the different crystals from the valine, leucine, and isoleucine. The mainly plate. Some plate is really thin, and some is thicker. Okay, some is thicker. We studied the temperature and salt substrate distance, right? Their effect. The temperature are known to play an important role in the crystal nucleus and growth. So the effect of the substrate temperature was studied as the pressure was kept constant. The pressure kept around 1.3 Pascal. And then we got some sheet, like here. The valence sheet is around, with a width around 1 to 3 micrometer will form, and the temperature as low as only 40 degrees Celsius. And you can also got the sheet around 80 and even 120. And we can observe even like 150 and even higher. But when you increase the temperature too high, you will not see those structures. We also pay attention to the distance between the substrate and the source. And around the wings, it's very narrow, like 3.5 centimeter. You got some structures, 12 centimeter, a little bit when you're too far away, and no material observed. Okay, just a film, just a film. So the distance is also important. Based on our observation, we proposed a modified SK growth mechanism. Okay, basically, in this case, when the molecules deposit on the substrate, they form a lot of nuclei and then eventually they form island, and eventually they will form because of lattice mismatch, you cannot got completely covered. Okay, and they form some island. And when the string effect is not that strong, you got started to have some crystals on those islands because the different surface energy, they will have the vertical growth. They got some vertical sheet. Okay, this is not exactly the same as conventional film, SK growth for the film, because here eventually we're not getting a film. We got some micro sheet array. That's why we call it a modified SK growth mechanism. Okay. Not only like the dipeptides and some other, the amino acids, even more complicated peptides can also be self-assembling. Okay? Like we know the collagen is an interesting, protein, right? And the collagen also have a pretty good piezoelectric property. People find out its property is related to the so-called HYP hydroxyproline phenylalanine. Okay, this is a tripeptide. Okay, and this is the chemical structures. Then we put it this way into the study. We also got self-assembled some wires. Okay, and because of their structure, we got some chiral, spiral kind of structure. And their piezoelectric property is also pretty good, right? It's over 20 picometer per volt. Okay, the hash rate is around 27. Okay, and their piezoelectric voltage content is extremely high. Right? For the piezoelectric constant, we have a different, ways to measure it. For its piezoelectric voltage constant, it's even higher than the PZT-based ceramics. Okay? And so this material also, all those studies show us for the amino acid, dipeptide, tripeptide can be self-assembled into interesting structures and have many interesting properties that has also been discovered in these materials: mechanical, optical, piezoelectrical, semiconductive, etc. Okay. Next, we will try to fabricate some devices. Clearly, this material can be fabricated into different devices. In today's talk, I mainly will talk about the so-called nano generators, that is, energy harvesting devices. Okay? And I will give you a very brief introduction of the history of the nano generator, and followed with a piezoelectric nano generator based on those biomaterials, and followed with a triboelectric nano generator and a hybrid nano generator, etc. Okay. The piezoelectric property is quite simple. Basically, when you stress or compress it, you will have some polarized charge on the surface. So realize the mechanical energy into electricity, conversion. So we try to harvest this electric energy. The first energy conversion is nanomaterial was demonstrated by Professor Zhongling Wang using the atomic force microscope. Right, with the AFM probe, deflect the zinc oxide nanowires. As the energy is converted, that's why they observe a lot of electric signal. Later, while I was still in Professor Johnny Wang's group, and me and also Dr. Yongqing, we work together, fabricated the first nano generator using the potential along the length, the lateral one. So we got the AC nano generator. And this generator can also be harvested energy from some animals, right? Because the biomotion. Clearly, we have a plenty of mechanical energy from the biomotion. Okay. And how about the FF, right? The biomaterial. They also buy piezoelectric property. Could they convert mechanical energy into electricity? Could we fabricate some devices? So the device fabrication is straightforward because we have experience with zinc oxide based nano generators. We just fabricate the device and did the test, and then we find out we do have some voltage output from this device. It's over 1 volt. That's pretty good. How about compared with some other material like a virus-based generator and zinc oxide-based generator? Clearly, the output is much higher. Another difference is we got the plateau because the FF, they are dielectric material. There are no leakage current. Okay. And we also studied depending on the load and on the force, the power output. For the FF-based nano generator, the area power density is 3.2 nanowatt per centimeter squared. It's about 4 times higher than zinc oxide-based piezoelectric nano generators. So look like they got even better performance than zinc oxide. How about the stability? People always worry about the stability because the organic material we know, they are not, if you have a piece of meat in the kitchen, if you forgot it, and after a month, clearly it will be, you will got the mold, the smell really bad, right? The organic is, kind of decomposed. But for the crystals, they are really stable, right? They are really stable. And we did some stability tests. They can survive for many cycles. Okay. And we also try to drive some devices from this material, based nano generator. Here we are, connected this one with LCD, and look like this display can be powered by the power generated by the FF-based generator. That's good. Not only FF. Earlier, we have discussed many, self-assembled structure from different material like GW, FW, the tyrosine, etc. Different, amino acid. And we fabricated different nano generators, piezoelectric nano generators from self-assembled nano microstructures from those materials. They give us a pretty good performance. And for those chiral tripeptide, probably you still remember that collagen. That material can also be used to fabricate piezoelectric nano generators. Okay. And not only piezoelectric nano generator, we even fabricate some the carboelectric nano generator using this biomolecule assemblies. Okay, in this case, we studied the valine, the D type valine and DL valine, etc. And look like some material can get a higher output than the others. Okay, and in this study, the most important discovery is even for the same material, it can further increase its output. How? We're using the electric field during the growth. Earlier, we know if we apply electric field during growth, we can improve the piezoelectric property. But at the same time, because all the molecules are aligned in one direction, so that some of the positive charged amino groups will exposed on the top surface. That is beneficial for the charge accumulation and for the energy output for the TENG, the triboelectric nanogenerator. Okay, and we discovered that using the high electric field to drive the growth, and eventually the material give you much higher output than the material grow without the electric field, as shown here and here. Okay. And this clearly this device can be used to harvest energy from our body motion. Can also be used to drive different electronic devices. Okay. And finally, we eventually also fabricate a hybrid nanogenerator because we have fabricated the piezoelectric type of nanogenerator. We also fabricate a triboelectric nanogenerator. How about combine them together? Quite simple. We have 3 layers here, contact and separation, that is G and G, and we can have the energy output. If you further compress it, and then the piezoelectric will start to work. We call it the so-called PNG. So this is a hybrid nanogenerator. Okay, and here is the performance measurement. Okay, look like they did add up. So the hybrid nanogenerator is also possible for the bio based material, and we know the peptide or amino crystals, they are degradable. Okay, so the biodegradable. We need to take advantage of this property. So we try to fabricate some degradable nanogenerator using the biomaterial, and we did successfully fabricated the degradable PNG. And here is the performance, and on the right is the degradation, measurement. Okay, after around 25 days, they are dissolved in the solution. Okay, we tried different solutions as well, and here is the perspective of this nanomaterial and applications. Basically, we studied the self-assembly process from the biomolecules, including the amino acid and peptide, etc. Basically, moleculize. Okay, some natural biomolecules, and this material can be self-assembled into different structures, and also many interesting properties has also been discovered from this material. We try to fabricate different devices. In today's talk, we mainly focus on the energy harvesting device, but their capability is not limited to that. They can also be fabricated in some other devices as well. And just for the energy harvesting device, we have plenty of mechanical energy in the environment, right? Including our body. We try to use the energy harvested by the biomaterial-based nanogenerators to power different devices like implantable device, wireless sensor, etc. And so I have this privilege and honor to show you all those beautiful pictures and interesting research results. But definitely, I need to give thanks to many different agents and also peoples. With that, first I would like to acknowledge all those founding agencies from the founding agencies from like NSF while I was working in the America, and also in SFC and university, etc. While I'm working in China now, and also thanks to all my collaborators, particularly my PhD advisor, Professor Zhongli Wang, and also my long-term collaborator, Professor Ihad Great in the Tel Aviv University in Israel, and many others. And I like to thank all my group members. They're working day and night. And also my former students, particularly like Zhenzhu, Wu, and Hui Yuan, etc. Okay. Finally, I would like to thank you for your attention. to listen to my talk. And again, I really want to collaborate with any people, and everybody is invited to visit my group at Xidian University so that we can further discuss it. If you have any questions, I'm available right now. Thank you.
Dr. Kim, you mute.
Wonderful. Wonderfully interesting talk, merging biomolecules, self-assembly, piezoelectricity, and nanoscale manipulations. Now we are in the session for questions and answers. And I, in fact, have one short question. It was wonderful to see that some biomolecules can actually help design bioimplantable, piezoelectric devices and different functionalities. Now, I wonder, can we design some bioimplantable piezoelectric devices made of biomolecules so that we can have superior biocompatibility? That would be my first question.
Yeah, thank you. That's really a very good question. And that is also one area we're working on. First of all, such experiment has also been demonstrated. For example, Professor Xidian Yang at University of Wisconsin Medicine, they fabricated some crystals from the glycine. Okay, that is another glycine amino acid, and they also fabricate some they harvesters from this self-assembled material and embedded in animal, and so look like it's biosafe. And currently, my group is also working on this type of application because we want to take advantage of its bio nature, right? They are biodegradable, they are biosafe, and after the degradation, you eventually form the amino acid, that kind of nutrient, right? So that will not do harm to your body. So definitely, it's doable. Thank you for the question.
Wonderful. And and the second question is rather simple. As a young scientist award winner yourself, would you have any advices to younger scientists in designing their own research field like you did?
Yeah, so I think for this one, different people, I would say, will have different answers to this question, and different people will have follow different paths to achieve success. Okay, and for me, my suggestion will be, kind of no matter what you do, you should be self-motivated. Okay, you definitely need to do something you like. You're not, nowadays I can see, like for some students, they are kind of just study for their degree, right? Just to do some work asked by the advisor. So that is my feeling. Not all, but some students like that way, and I don't think that is a good attitude. If you self-motivated, if you love what you are doing, you will be more creative, right? When you encounter some obstacles, some challenges, you will find some ways to overcome. Instead of waiting for your advisor, waiting for your classmates to help you to solve that. If you self-motivated, you will, engage in the research you are doing, and eventually you will find what you are really interested in. Because early days, you just do what you are asked to do. Maybe that is your interest, maybe that is not your interest. But when you engaged in what you are asked to do during your master study, PhD degree study and even postdoc work, and eventually, hopefully, you will find what you are really interested in, and from there you can develop your own career, develop your own research field.
Okay, yeah, maybe I can add in my words here. Actually, in last 10 years, I see Rusen grow up. Yeah, I can feel that exactly Rusen, how love his work, Yeah, not only he make all this kind of wonderful work, every picture was so beautiful. Yeah, another thing is I talk to Rusen very frequently. I think in last 2 months, maybe, yeah, more than 10 times or something, we met online, always in the midnight. Yeah, Rusen was almost living in his office, Yeah, I said, what are you doing? I'm writing proposal. I'm writing papers. I'm editing all this. You can say that I feel, he put all his love there. So that's how he made so big, achievement. Because Rusen was a young scientist, and we really are surprised about how many paper you have published, how much citation, the numbers is really high. So many times I think, even the people didn't matter Rusen think he will be a very kind of older one, right? Yeah, but it's a really, really young one. Okay, so Rusen, I have another question for you. I see you are in material school, right? Yeah.
Yes.
So yeah, you did a lot of work also from basic of the materials, how to synthesize the materials, how to modify the properties, how to enhance all these properties. I see in one slide is very beautiful. You are modifying and enhancing the property was by the PVD, right? Yeah, you do the process with PVD, right?
Yes.
Yeah, it's a PVD. But I have a question. It's normally, PVD sometimes means the material property is not that high, because, the density and education and all these issues will be happening, the PVD is not the best choice. But can you give me some reasons why you choose the PVD as a major, approach? Yeah.
Yeah, so this is very very interesting point. First, I would like to thank Alex for her kind of comments on my past. And to be frank, I really love what I'm doing. That's why I spend a long time, day and night, on what I'm working on. That's why I feel really sorry for students who just simply do what they are asked to do, not engaged in the work. And second, to the the question about the PVD. And normally, earlier we mainly using the solution-based approach to grow the material, and we did got a lot of interesting structures and very good properties, and we also try to improve the enhance the property using different strategies. Just like earlier I said, one process will be co-assembly, etc. But lately we're also using the PVD process, the vapor deposition, and vapor deposition definitely have a lot of problems. Earlier, just some problem Alex has already pointed out, like the adhesion between the material and the substrate, and etc. Right, the density. And not only that, in this study, we also studied the temperature effect. Cannot be too high, cannot be too low, and the distance cannot be too far, cannot be too close, etc. Definitely, it has a lot of problem. But why we still try this PVD process? Because in the study we found out that the PVD process and the solution-based process, they are not give you the same, sometimes not give you the same crystal structure, because the material, like particularly like the protein and the peptide, we know all those amino acids, they are not like the inorganic material. We know, we are quite familiar with the inorganic. We have the the phase center cubic and body center cubic, etc. All those atoms, they are stacked, very nicely to form the crystal structure. But for the amino acid, eventually from our body, they have a different secondary structure. They call the beta sheets. Basically, they just they just one after the other, they form a kind of a sheet structure, kind of, and they also have a so-called alpha, helix, they kind of a spiral, right? Basically, they have a very, interesting secondary structure. That's why our body, so powerful, basically. And sometimes they also cause a lot of problem. And we found out, people also found out that the PVD process, the vapor deposition and the solution base can give you different crystal structure. And so when you use the vapor deposition, method, then you can fabricate a different crystal structure, different crystal structure or different morphology from the same material, same amino acid, so that we can study, what kind of opportunity we can have, what kind of property we can achieve from the material. For example, the FF, diphenylalanine, for this type of material, when you in the past, when we grew in the solution, we got the piezoelectric material, piezoelectric property. But when you grow with the vapor deposition, maybe you got a different crystal structure and you do not have the piezoelectric property. But however, although you do not have the piezoelectric property, maybe you have some better physical property in some area. Right, so that's why we want to explore all the different growth process to get, maybe kind of a more material with better property in different areas.
Okay, that's very nice answers. Maybe I follow up for this. So, how higher the temperature you can go is 120 degree?
Yeah, for the growth, normally we can grow like lower temperature or high temperature, but we cannot be too high. Like 100 is okay, and sometimes 200 is also even okay. Okay, but if you got too high, definitely you will all those organic material they will decompose, right? And we also studied the thermal stability after your growth. What's the temperature this material can survive? Some can survive lower, some can survive higher. Some you can survive even around 300 degrees Celsius, right? So some is really thermal stable, but some is not. But at this moment, we are just fabricate devices and do some tests. At the same time, we also do some computation. Hopefully, can give us some guideline, because this type of material is relatively new. So there are not a lot of theories for us to help.
I must think about that, Rusen. Maybe this was a suggestion or comments or something we can try. Yeah, after the PVD process, right, the temperature, as you said, couldn't go higher. So sometimes the material's property may be not that good, right? Sometimes the morphology may be not exactly what we want. Maybe in the later you can add in a process, a step as like a very rapid, the annealing. Yeah, the same like that. Very short time, temperature not damages the materials, but reshape, the shape, geometries like this. Yeah, just think about this.
Yeah, that's very nice point. I think it's really important, like post-growth treatment, like for the traditional, we know like annealing process and some other heat treatment may improve the property of the material, and it's really common for the traditional like steel, some engineering material, and some of the strategies may also work for those biomimetic material as well. Thanks for your suggestion. Definitely, it's worth a try.
Yeah, I like the structures. You make so many beautiful structure, like the cactus, like that beautiful. And the last, slice you show is really, really good. Yeah. So I like
Thank
all
you.
these things. Yeah. Sente. Yeah.
Yep. One short last question would be usually when we think about piezoelectric materials, I tend to think about hard ceramic materials. Now that because you can make biomaterials based on self-assemblies, do you think we can possibly have some soft and flexible material that also exhibits piezoelectricity? I mean, this is just a random idea.
Yeah, that's a very good point. That's a very good point, and that's also one important reason we work on those biomaterial. We know for the traditionally piezoelectric material is mainly dominated by those ceramics like PZT, right, and
Right.
PMNPT, right, those are relaxer, and another it will be BTO, right, barium, titanium, etc. Right. Earlier in this work, I also talk about the PPLN, lithium niobate, etc. They all ceramic is really hard, right? They're really hard. But for the biomaterials, their Young's modulus could be much smaller, right? So it's really possible to fabricate some, flexible, much softer piezoelectric material. With those softer piezoelectric material, clearly it's possible to fabricate, flexible piezoelectric devices. It's really possible. And in addition to that, take advantage of its bio nature, right? And maybe it's can play some important role for the wire technology, right? Wearable technology, or maybe implantable, devices, etc. It's also they all possible. I think that's really a lot of things are waiting us to explore.
Yeah.
Wonderful.
I think this will be very nice, Yeah, if you can make this, will be a big, kind of future can be made because not only, generators, yeah, sensors, actuators, all these kind of things can be happened based on your material.
The contact info on my website, right? So collaboration is always welcome.
Maybe I can add in another question. Is okay, Dr. Kim. Yeah. So, Rusen, I see you picked your slides was so beautiful. Since the first one, right? Yeah, you make a lot of what kind of like artist. Yeah, the pictures. So not only science, right? As looks like very beautiful drawings. So can you tell us some secret?
Yeah. The main reason is I would say, early days I like photographer. Basically, I like taking pictures, and I used to not have not now. After come back to China, I did not bring my camera with me, and yeah, I used to like take hundreds, thousands, and even several thousands pictures. Well, first, at the early days, I work on the nanostructure. So the SEM is just across my office, and the TM just like 10-meter, distance from my office. I just go outside my office and enter the SEM room, take a lot of SEM pictures. And for the TM, early days, we're still using the films. Probably the new people do not know they have the so-called negative film. We have to work in the dark room, follow all of the process, and later we have the digital, make it easier. So I take a lot of SEM pictures. In the past, I did some statistics. At least, several tens of thousands of pictures for the SEM and TM. And I also have a pretty nice camera, the and also take my pictures of my kids and the nature, and so sometimes I'll do a little bit touch up on the pictures. So just my hobby, just my hobby.
Okay, that's very nice. Really makes sense. Otherwise, if you don't have this, taste or some, long time trainings, it's really hard to make so beautiful slides. Yeah. Also good. Go back, take some more pictures. Okay. Yeah. We need to, all go back, take more pictures, found a beautiful thing. So, maybe we can, have another channel is to compete for the best, science pictures.
That's
So
good idea.
Rusen should be, win that. Yeah. Okay. Rusen, almost into the show. Yeah, I think, I ask one question is for the young scientists or the young students. You say most importantly, to do what you love, right? Yeah. But now the thing is, a lot of people don't know what they love. So how you found it? How you found it you love, right? That's that's kind of a chicken check egg, right? Yeah, how you found it? For example, yourself, how you found it? Yeah.
Yeah, that's really, kind of very, this question I would say very difficult to, to answer, but I try my best just give you my, 2 cents. And I really agree with Alex. Nowadays, people, many young students really kind of lost. Do not know what they like. They just, go to the college from high school, all natural, and they find a job. If they do not find a job or for whatever reasons, they go to the graduate school for the master, and maybe for whatever reason they continue to as a PhD. Maybe they are not really doing for not motivated to do that, just for some other reasons. Okay, and back to the question, how young student find what they love. I would say first try to do engage in the research you are asked to do. Okay, so that is one thing, so that you can develop some necessary skills. Okay, so you are familiar with the area. Like for me, I'm mainly work on the experimental part, and do just what you are asked to do. Then you know how to use SEM, TM, XRD, all those characterization equipment. And from the growth point of view, you're familiar with the solution growth, vapor deposition growth, etc. You know all those skills. Okay, but maybe the material you asked to work on is not your interest, right? I'm working on the biomaterial. Maybe the student not interested in the biomaterial. Maybe we're interested in some other material. Maybe one student asked to work on one device, and maybe that is not what they really interested. But from this work, they are familiar, right, themselves with all those skills, and they can start to explore, and maybe reading the different papers, attending the conference, talk to people, and maybe they will somehow, I believe somehow they will start to have their own interest, right? Something they're really interested in to do. At that point, they already master all those skills, or most of the skills they are required to work on the new topic, right? They know how to synthesize the material, how to characterize the property, how to fabricate the device, no matter what kind of device they are interested in. But a lot of skills, they are common. They are kind of shared skills, right? So my best suggestion is, engaged in what they are, required, asked to do, and try to, master all the skills during this process, and start to explore widely, or talk to people, attending conference, and one day they will find what they love.
Okay, that's very nice. So, Cynthia, can you tell us your story? Yeah, because in Korea you have a lot of choice. Yeah, you're good looking. Yeah, you are smart, and you can easily go to be a movie star or something. Yeah, so why you choose your job? How you found your love? Yeah.
First of all, thank you for calling me all those things, but I will not have made a movie star. I know that. But that's a great question. So I remember when I was a high school student, I told my parents that I want to major in material science and engineering. And my father's reaction immediately was, why do you want to do that? Do something more famous, to electrical engineering or to mechanical engineering. So, and I was somehow determined to do material science because I somehow liked it better. So that kind of little, I mean, as a high schooler, I probably didn't know what material science was at all, right? But but sort of being bold to choose something that you feel seems good sometimes leads to the right directions, I think. So what I think is important probably would be to not be afraid. It's okay to it's okay to just give it a try. If you don't like it, you can always change it later. So I think it's important to try more things out, and then you can always fail and then restart. That's not uncommon. I mean, I changed my thesis, PhD thesis project like 3 times, and I somehow
Three times.
graduated. Yeah.
That's not easy. That's not easy.
Okay, got it. Yeah, 3 times they changed the topic. Eventually got the degree.
Yeah. Yeah. Yeah.
Okay.
So I think just trying out is important. That would be my my story. Yeah.
Oh yeah, I love that answer. Both of you have gives a good answers to the students. I think many of, because this morning I do some PhD pre defense or something. Yeah, I can feel that a lot of students was really now is confused with this. It's really my career should be this path or something like that. They never don't know. When you are young, sometimes, you even, don't know what's the future. So dynamic, everything. So a lot of things was happening. I think, Rusen gave first, if you are graduate students, if you are young, first you just focus on the things you asked to do, you have to do, right? You have to finish. You was asked to do. So you just, get to that, engage with that. I think put yourself in, that's more important, right? Because put yourself in, you could get the real skill, right? You can get the real point. Otherwise, you couldn't get it. Another thing is like Sante said that if you choose this, when you put yourself in, you eventually, you make it, or you never make it. You also can change. Don't worry, right? Yeah, you have a lot of things you can try. Yeah, that's very important. But my worst is okay. Tell myself I can. Yeah. So every day, 3 times, I tell myself, okay, I can, I can, I can. If it's a hard day, it's a hard job, I tell myself I can. This is like a magic. You know why? It's not a magic word, but this really keywords is when I say yes, I can. So I just shut or close the excuse. No excuse, right? You can. You must do that. So when you say to yourself, I can, I must make it. Okay, that's no excuse. You just, go to that target. Yeah, that's my secret. Okay. So Sanjay, yeah, time fly. We almost too close. Yeah, to the end.
Yeah. Okay, let me now move on to the delivery of the certificate. So I hope the screen changes pretty soon. So let me now deliver the ICANX certificate to Professor Rusen Yang for the wonderful talk. Professor Yang, here is your ICANX certificate, and we thank you very much for the wonderful work and the wonderful talk.
Thank you, Pante, for the certificate, and thanks, Alex, for this invitation, and also for this really wonderful ICANX this forum. I think I kind of follow this ICANX for many years. It really grew bigger and bigger, through the years. And here maybe another advertisement, for the Alex and. At the Xi'an this year, we will have another summit, kind of forum. It's also hosted by the ICANX. We will have, many, the people from the frontiers to talk about the science. People are welcome to visit Xi'an and for this ICANX summit. And while you are there, you're welcome to visit Xidian. How about that, Alex?
Yeah, very good. Thank you. Yeah.
Thank you. Thank you very much.
Great. Let me now gently remind you of the next ICANX talk next Friday. It will be delivered by Professor Xu Fang at Tsinghua University on flexible integrated circuits. So it will be interesting, so please stay tuned. And the talk will be moderated by Professor Lan Fu of Australian National University with 2 panelists and 1 challenger. So thank you again for joining ICANX this week, and I look forward to seeing you all next week.
不再是奇迹，不再是幻想，此刻真感觉全世界对我鼓掌，不必太在意身旁惊奇的目光，可以点点头，可以放声歌唱。我创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞，不再为曾经失败放弃或感伤，努力方向。I can， 我可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。I can。没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞，不再为曾经失败放弃或感伤，努力才是真的方向。I can， 没有什么可以阻挡心中无限的力量。I can。你也能够像